All right, welcome to my talk today. Today I'll be discussing the Bayesian Statistics Toolbox, or BST, building a robust, replicable Bayesian workflow for the behavioral and neurosciences. So my name is Hyosub Kim, and briefly about myself, I'm currently an assistant professor at the University of Delaware, where I lead the Sensory Motor Learning Lab. And fairly soon, I'll be starting a similar position at the University of British Columbia in Vancouver, BC. So research in my lab combines computational modeling, behavioral experiments, and neurologic patient testing to better understand fundamental principles of human motor learning and motor control. So in other words, I'm interested in how humans acquire, adapt, and refine motor skills. I also have a strong general interest in how we make our statistical inferences. And for that reason, I've recently started migrating our lab's workflow from a classical or frequentist framework to a primarily Bayesian one. I've also provided my contact information for you all. And right off the bat, I want to thank several groups and individuals for generously sharing their work and knowledge in making this project possible. First off, the PyMC developers for developing PyMC, the RViz developers who have a great visualization package, Jordi Warmenhoven, who's a data scientist and developed this great GitHub repository that BST essentially bootstraps off of. And then John Krushke and Richard McElreath, who, in my opinion, wrote two of the best introductory textbooks on Bayesian statistics. I also want to thank the PyMCon organizers in general for inviting me today. But in particular, I want to highlight three people, Rowan Schaefer, Austin Rockford, and Ravin Kumar, who've worked with me individually and really helped me shape this talk today. So as far as what to expect, first off, I have an announcement. If you have questions and or you want to discuss anything you've heard today, please go to this URL and post your comment or question on the Discourse page. And I'll be hanging out there, and I'll be there during the talk as well as hanging out there afterwards. So today I'm going to introduce the BST, its motivation, its rationale, how it can help behavioral and neuroscientists. And then I'll go through some preliminaries in order to get set up with BST. And then I'll introduce some behavioral data that was collected in my lab and that we'll be working with for the rest of this talk. And so we'll go through some worked examples of using BST together. And so each of these examples embodies some very common analyses within the behavioral and neurosciences, and they all sort of build in complexity. And then finally, I'll give my concluding thoughts and summarize what we did today. So as far as goals for this talk, I want to introduce BST as well as its rationale. I also am interested in demonstrating what I think is a sensible Bayesian workflow with BST in conjunction with PyMC as well as other modules like RViz. And then I want to discuss some pedagogical uses for BST because I think BST can be a great tool for those who are just starting off with Bayesian statistics or going through the Krushke textbook, as well as those who are more experienced. And then the overall goal is that everyone attending today will walk away from this talk feeling more empowered, more confident, and definitely more likely to use Bayesian statistics in your own work. So I'm trying to reach as many people as possible, and everyone is welcome to this talk. But in particular, I'm targeting students, people working in industry, and academics who are already familiar with frequentist statistics, but maybe want to learn and also do more with Bayesian stats. I'm also interested in reaching those who have a good grasp of Bayesian fundamentals, but maybe still rely on frequentist tests because at least the perceived startup cost to switching over to Bayes is too high. And so that was me for quite a while, and that's part of the motivation for developing BST, to lower that bar for entry. And then also I'm trying to reach those who are just starting to learn Bayesian statistics and maybe even just starting to learn Python and PyMC, and perhaps just need an extra little boost to get going. So I won't be teaching Bayesian inference from the ground up. That's just beyond the scope of this talk. However, I do have pointers to some excellent textbooks. I also won't explicitly try to convince you of the benefits of Bayesian statistics, I'm assuming that if you're here and watching this talk, you're already interested in Bayes and you have some intuitions as far as how Bayesian statistics may be helpful. But at the same time, I'll still be doing some comparisons of frequentists versus Bayesian statistics. So what is the Bayesian Statistics Toolbox? Well, concretely, it's a repository up on GitHub, but more specifically, it's a library of functions that take advantage of both Python and PyMC in order to run a spectrum of Bayesian analyses in a simple, straightforward manner. These functions are primarily wrappers for Bayesian generalized linear models, or GLMs. It's a module that allows you to run Bayesian analogs of some of the most commonly used frequentist tests. So think t-tests, ANOVAs, and regressions. And typically, BST allows you to do this with one-liners. Another way to think of BST is as model scaffolding for your own Bayesian explorations. So this is when you become more familiar with Bayesian stats and you want to have some starter code in order to work off of. BST can be helpful for that as well. It also makes Bayesian modeling more user-friendly, and I've done that by including several helper functions for taking care of some of the more nitpicky tasks involved in model fitting. So I have the full installation instructions up on the GitHub page. However, you also have access to this Google Colab notebook, and you should be able to run it from top to bottom. And in fact, if you click on File, you should be able to save a copy of this very notebook within your Google Drive. However, if for some reason neither of these options appeals to you, or you just want to try to install it locally a different way, I've provided the syntax in order to pip install the repository. And so here's a list of some common dependencies if you're working in the Python and Bayesian statistics ecosphere. And now, why BST? In terms of why was it developed and why might it be useful for you? Well, in terms of my own personal motivations, I wanted to start a sustainable, ongoing project that turned what I was learning about Bayesian statistics into something useful for my future self and future lab members. So originally I started working or learning about Bayesian statistics through the Krushke textbook. And I was going through the textbook along with the help of Jordy's Python PyMC 3 notebooks on GitHub. This is because all of those notebooks were in Python, and I wanted to do Bayesian statistics with Python as opposed to R. And so I also wanted to essentially create these modules or this library of functions to make running Bayesian statistics analyses more easy or more convenient. So essentially, I've wrapped these models from the original repo and put them inside functions and updated them to use PyMC4. And I knew that by doing that, I would be more likely to use these functions, these statistical models repeatedly. And then I later realized after working on this project for a while that there are probably lots of other people like me for whom this module would be helpful. Thinking of broader motivations, I think BST helps lower the bar for entry into using Bayesian stats, in particular for behavioral scientists, as well as neuroscience researchers. I know from experience. I think BST can serve as a nice bridge between learning to code things up from scratch to the super flexible modeling that you can do now with Bambi, which is a great Python library module that provides a Bayesian modeling interface. And along those lines, BST should be especially helpful for those Python users learning Bayes with the Krushke textbook. And then the other motivation was to make it less tempting to fall back into frequentist habits and using one-liners with stats models. So as illustrated here in this cell, I'm showing you raw PyMC code for running a best test, the Bayesian analog of a t-test. You know, it's about a dozen lines of code and there's nothing too crazy, but compare that to running a one-liner from stats models. And so in terms of my motivation, I wanted to make BST just as easy to use as these one-liners from stats models. So I'm just showing you the syntax for using BST and running the best test. So I've already ran this notebook, so hopefully you have as well, and all of these libraries are imported. I included the BST functions within this notebook specifically so you wouldn't have to go to my GitHub repo and install it yourself. So I wanted to make this talk frictionless for those who are new to using PyMC. And so for the examples that I'm going to talk about, we're going to use BST to analyze the data. But speaking of the data, just to describe them and to give you some picture in mind of what we're actually analyzing, these data actually come from my lab, from a behavioral reaching experiment that involved 10 participants with Parkinson's disease, which is a neurodegenerative disorder that affects motor and cognitive function, and data from 10 age-matched neurotypical controls. So the question was, how does PD impact motor planning? In order to test this, we had participants make reaching movements at this workstation, illustrated here. They're instructed to make fast, accurate reaches to different visual targets displayed on this horizontally oriented monitor, while sliding the stylus along the graphics tablet below the monitor. So the tablet is how we track their movements or kinematics. No visual feedback at the hand position was provided until the end of the reach. And that was to prevent people from making corrections while they were moving. We were interested in how the motor plan is made. And so I don't want to get too deep into the weeds regarding these data, but I think just to enliven the discussion and to motivate the examples, I'll just give a bit of background and theory. So it's been shown that the motor system independently plans movement extent versus movement direction. So these two things are modularized. PD causes many different motor impairments, including hypometria, which means making smaller than appropriate movements. So we hypothesized that PD should selectively impair errors in movement extent, how far they're reaching. The specific prediction is that we should observe hypometric errors in the PD data, especially for the far targets. So I included two target sets, a near target set and a far target set, defined by their distance from the starting position. Just a quick disclaimer, we're not the first to study this type of question. The data are provided here as part of a larger study. So this is just one of several analyses. The purpose of analyzing the data here is primarily to motivate using BST and using Bayesian statistics, and also to provide concrete examples of how to do so. So I think people from the behavioral sciences especially, and from neuroscience will be able to relate to these examples. But hopefully with my descriptions, everyone will get a sense of what we're doing here. So in this figure, I'm showing you individual data from an age-matched control. So we have X and Y axes, and it's like we're looking down onto the workspace. And so the magenta dot represents a start position for all reaches. The green circles, dark green circles, represent the targets. I said there are near targets, which is this first array of targets, and far targets, which are twice as far away from center as the near targets. The colored dots represent all of the endpoints for the reaches for this one subject. So you can see the variability of where they reached. I'm just plotting the error ellipses on top of them, so you can see the pattern of errors made. And in this case, with the age-matched control, yes, you do see variability in the reaches, but on average, they're reaching fairly accurately to the targets. Here's a representative PD subject, and you can see, first of all, that there's greater variability in their movements. And then specifically for the far target set, you can see that the centroid of the ellipses would fall short of the target distance. So they are making shorter reaches than they should be. And some more details are provided in this caption. So we're going to import the data first. Here is the legend for the subject for the different variables included in the data frame. Of note is the grouping variable, which indicates whether the data is coming from a PD or an age-matched control. The target number, so targets 0 through 7 are the near targets, and targets 8 through 15 are the far targets. And then our main dependent variable is this distance constant error, which means the average error in terms of movement extent. So I parse the errors into errors in movement extent versus directional errors. And for these examples, we are only concerning ourselves with the errors made in movement extent. And the intuition is a perfectly planned movement in terms of distance would have an error of 0. Positive means an overreach. Negative sign means an underreach. So just a light processing here to load some data frames for the different analyses. And now our first example, the comparison of two independent groups. This sort of analysis is perhaps one of the most common within behavioral science, where you're comparing the performance or the effect of a drug, for instance, on one group versus another. So from a classical statistics perspective, we'd run a t-test. Bayesians would do parameter estimation, and in this case specifically, what we refer to as the best test. Our goals are to compare errors in movement extent between participants with PD versus age-matched controls for the near target set only. I'm going to compare frequentist analysis to Bayesian parameter estimation, also compare raw PyMC code to BST syntax to show you the purpose and usage of BST. So first of all, I'm plotting the data. Here's a histogram showing you on the x-axis the errors and on the y-axis the counts. So we can see qualitatively that, in fact, the PD subjects seem to be hovering closer to an error of 0, and the age-matched controls appear to be overreaching more on average. And we'll unpack that a bit more later. So as far as running a t-test, we would do that with SciPy. Again, it's a one-liner. What does it output? The t-test statistic, as well as a p-value. So what does this result tell us? Well, from a frequentist perspective, this means that under the null hypothesis of similar errors or equal errors between groups, there's an 8.5% probability of observing a difference of this magnitude or larger due to chance alone. So since alpha values are typically set at 0.05, if we were writing a manuscript, we'd say our p-value here is 0.85, and the results are not significant. In other words, there's not enough evidence to reject the null hypothesis. Well, how can we answer this question with Bayesian statistics? So now we get to the fun part. And first of all, let's note that in this section, I've adapted code and text, adapted from a great notebook that the PyMC developers have put out, which is essentially a Python port of John Krushke's well-known paper on Bayesian estimation. And so the basic idea is that we want to be able to go beyond these binary decisions about significance or significant findings versus not significant findings to actually estimating parameters and quantifying the uncertainty and quantifying the credibility in different parameter values. So the first step in a Bayesian approach is to specify the full probability model, also referred to as a graphical model, that corresponds to our actual problem. And the point of this talk is not to go into great detail with the exact modeling mechanics, because the focus is on using this new toolbox to help you with your inferences. But I will talk, at least at a high level, about these models. And so here, this figure is taken from the Krushke textbook. We're going to start from the bottom, which is depicting the likelihood function. So this is the function that's generating the putative observations. And so we're choosing a student's t distribution to describe the distribution of errors from each group. The rationale for that is that the t distribution is less sensitive to outliers than a normal distribution, which might be the default choice. I've provided the equation for the t distribution. What you really want to take note of is that there are 3 parameters. 2 of them are in common with the normal distribution. We have a mean, mu, and a precision or an inverse variance, lambda. And then we have this third parameter for the t distribution, which is called nu. So new essentially specifies the normality of the data, and larger new values make the distribution more normal. I'll note that there are two separate likelihood functions, one for the PD group and one for the age-matched controls. You can see how they're parameterized here. Note that the new parameter is shared across the two groups, and that's an assumption we've made within our model, whereas we're estimating separate mu's and sigmas for the two groups. We're applying normal priors on the group means, and then we arbitrarily set the hyperparameters to the pooled empirical mean of the data and twice the pooled empirical standard deviation, just to scale the parameter estimates correctly. And note that these are very diffuse priors that should not bias the estimates a priori, meaning not bias the estimates towards age match versus PD. So here we're creating the model from scratch using PyMC code. You can see here we're defining the model and then assigning the distributions for the parameters. Again, not going to go into great detail with this, but just giving you a high-level view. Similarly, for the standard deviations, although for the SDs, we're going to assume a uniform distribution. And then for new, we're going to assume an exponential distribution with a mean of 30. And the rationale is that we want to choose a distribution that's positively valued because new can only be positively valued. And then we want high prior probability over regions of the parameter that describe the range from normal to heavy tail data under the TE distribution. And so this is what the prior looks like for new. And then a technical note, we're transforming the SDs to precisions or 1 over the variance before specifying our likelihoods. And this is a PyMC syntax specific issue. And then we can extend our model definition by computing the actual contrast or comparisons of interest, which include the difference of means, difference of SDs, as well as a standardized effect size. And this is so that we can evaluate more specifically the effect of PD on movement control. And then finally, we fit our model and we will eventually evaluate its output. But up to this point, we've done all the modeling steps except evaluate the model output. And so we're going to pivot now to show how to use BST to perform all of these previous steps, as well as the remaining steps that are involved in a Bayesian workflow. So we're going to run the best test using BST. So what are the issues? Why do we even want to run the best test using BST? Well, first of all, having to code up a model like this from scratch, fairly simple model, even if you're copying and pasting the model each time you want to run it, that's going to be cumbersome. And this is a fairly, common sort of test that you would want to run. And so let's try to make it easier for people. The second issue is that this type of friction of, the cumbersomeness of coding it up from scratch or copying and pasting each time increases the probability that you're going to fall back on what you already know and are comfortable with. And I say this from experience because that was historically the main barrier for me in terms of not switching over to Bayesian statistics, is that it took time and it took a lot of energy at times when maybe I didn't have that energy just to do a comparison of two groups. And so for most of us, this would mean that we're going to use a SciPy t-test. But the solution then is that if we use BST, we wrap the model in a function so you get the convenience of running one-liner in conjunction with flexibility in model specification, which I'll show you in the next example. You merely have to call the appropriate function. In this case, we call it best as a tribute to the original authors. And then note that BST tries to enforce the use of tidy data by requiring the two inputs to be the outcome variable and the grouping variable, rather than entering separate variables for the two groups' outcomes. And this is a common theme throughout BST, this issue of enforcing tidy data. Note that you can increase the number of draws by setting the end draws argument to whatever value. And then most importantly, note that BST always returns exactly what you need to visualize and diagnose your model, which are the inference data and model objects. So essentially, I want people to make decisions based on principles in terms of what sort of tests that they're going to run, as opposed to what's most convenient. And again, I'm saying this from experience, and so I hope BST helps with that. And so here again is the syntax for running the best tests using BST, outputting the model as well as the inference data objects. So what do you do after you actually fit your model? Because we're talking about a replicable and open Bayesian workflow, I'm going to go through those steps, not all of them, but definitely hitting some of the important ones. And one of those is to check the health of your MC-MC chains. So the sampling process involved in calculating the posterior. And you can do that with an rviz function, plot trace. I won't go into detail with what we're looking at here, but I do want you to note that qualitatively, we see signs that our sampling worked out well. And what are those signs? Well, in the left panel, we're looking at the marginal distributions for the posteriors for the parameters of interest. And then we can see in the left panel that there were two MC-MC chains that ran in Google Colab, and there's large agreement between those two chains. In other words, those posteriors are quite similar. In the right-hand panel, we see that sampling was more or less stationary, meaning that there were no sudden drifts or jumps in the sampling process. So the right panel shows you sequentially the samples. And so we can see what are sometimes referred to as hairy caterpillars, which is what you want. Again, this is just a high-level view of what you do and what you're looking for. For much more detail on diagnosing your MC-MC sample traces, I would refer you to the Krushke and McElraith textbooks. All right, now on to the fun part, which is looking at our posteriors. And so here I'm plotting the marginals for the different parameters of interest. And actually, so we're using rviz's plot posterior function, which replicates the histograms that you see in the Krushke text. We're summarizing posterior distributions of the parameters and presenting a 95% credible interval, as well as the posterior mean. So the 95% credible interval, or highest density interval, is indicated by these black horizontal lines. And then the means are reported as well. And you can see the values that are output. I'm going to move on though, because really in this model, what we're most interested in are the specific contrasts, which, if you recall, are the difference of group means, differences of group standard deviations, and the standardized effect size. And so that's shown here. And in orange, this is reporting how much of the probability density, the posterior density, is on one side or the other of the reference value. And in this case, I chose a reference value of 0. And so I'll summarize our findings in just a moment, but I also wanted to show you another view of some parameters, or sorry, some contrasts of interest. So again, we have the difference of means and difference of standard deviations. But in addition to quantifying the posterior in terms of a reference value, I'm also providing how much of the probability falls within a region of practical equivalence, or a rope. So another great strength of Bayesian estimation is that we can quantify evidence in favor of equality, or a null hypothesis, something that is much, much more difficult in frequentist stats. So our interim conclusions from this analysis are that it looks like there's differences between the two groups for all three measures, but they're not very robust. You can see that the majority of the posterior is on one side of 0, 92.1% in the case of the means, but we still have 8% on the other side of the reference value. So concretely, if this is a comparison between the age-matched controls and the Parkinson's patients, which it is, it means that there's a 92% probability, according to our model, that the mean movement error for the age-matched controls is larger than the PD subjects. But on the other hand, there's an 8% probability that the movement error is larger for PD subjects relative to age-matched controls. So again, the majority of the posterior would suggest larger errors for age-matched controls, but it's not bulletproof, essentially. So we used 0 as a reference value. We saw the cumulative probabilities for the posterior. So I just explained the cumulative probability of 92% for the difference between group means. The effect size and differences in standard deviation are similarly positive, and there's a similar cumulative probability as well. So it appears that the age-matched controls tended to make larger errors than PD subjects for the near targets. This is perhaps counterintuitive and something that we'll unpack a bit more later in the talk. What did we learn from this example? Well, based on the probability model we specify, Bayesian parameter estimation can provide much more information than a t-test, clearly. We can quantify the uncertainty around all the parameter estimates and quantify the credibility of different parameter values. BST provides convenience functions intended for repeated use, again, hitting this theme of replicable workflow. And then just to be very concrete, with BST, we use 3 lines of code in order to fit our model to data, diagnose our model fit, and also visualize the posterior. The vast majority of what we would want to do in an analysis such as this. So in our next example, we're going to go through a repeated measures design. In the previous example, for each participant, I pooled all of their data for reaches to targets of the same distance. So essentially, I'm treating all the data for the 8 targets as though they were all the reaches were made to a single target. And this was to improve the estimates of individual subject behavior. So using more data to estimate the movement extent error. However, one could argue that pooling the data like this is only justified if we can show there's no credible effect of target location first. And so in this example, we're going to run this exact control analysis. To simplify things further, we're only going to focus on data from the PD group. We'll eventually get to including all of the data in the third example. So in this manner, I'm building in terms of complexity with each example. As far as the model, we're dealing with a situation in which each participant undergoes several different conditions, hence it's a repeated measures design. We want to model the effect of target location, which is the within subjects factor, on the same dependent variable as example 1, the movement error. We're going to compare errors in movement extent between all 8 target positions for the near target set for only the PD subjects. We'll again compare a frequentist analysis to a Bayesian statistical model. We'll show how to do this using BST, and then we're going to show how BST can serve as a helpful starting point for further data exploration. So expanding on this idea of BST providing model scaffolding for your own customized model. And then I'm going to add another step to the workflow by including an example of a posterior predictive check. So here's the stats model's one-liner for the repeated measures ANOVA on these data. And so what does this analysis tells us? Here's the ANOVA table. Well, with a p-value of 0.42, this suggests there's not enough evidence to reject the null hypothesis of an effective target location. So beta represents the effective target. So in other words, there's no strong evidence that errors were dependent on the target angle. How can we estimate the effect of this within subjects factor, target location or target angle specifically using BST? I'll show you the exact syntax in a moment, but first we'll specify our probability model, here shown as a series of equations. And note that up top, we're using a normal likelihood for this problem, for this example. And then we're modeling the expected value, mu, as a linear combination of a baseline deflection from 0, beta naught, a within subjects factor, xw, and a subject-specific deflection, xs. And then we have our coefficients on those independent variables as well. Notice that there are priors for sigma W and sigma S. So in other words, we have priors on our priors. So here we have sigma W, which is defined as a gamma distribution with alpha and beta shape rate parameters. And so that's what we mean by having a hyperprior. We assume in this model that knowing about the effects of one target on movement extent errors, or knowing the subject-specific deflection, should improve our estimates of others. In other words, if I know what the errors are like at one target, I'm assuming that the errors at other targets will be similar. And so there's a pooling of information in order to sharpen our estimates. And that's an assumption of the model. This type of hierarchical or multi-level modeling is an excellent way to extract as much information as possible from your data, especially if you assume this commonality between, for instance, the different target locations or the different subjects that are being tested within the group. So PyMC developers, again, have a great host of resources on this topic. And then again, in this example, we are using diffuse uninformative priors. And so this is a common theme throughout BST. The priors are, in most cases, the exact same ones used in the Krushke textbook. And there's a reason for this, and that is that we want to start off with skeptical priors, ones that would get by the critical eyes of a reviewer or a critical colleague who doesn't want to think that you're biasing your posterior estimates with a more certain prior than is justifiable. Of course, there are instances of using more informed priors. There are principled reasons to do that. And I think in a Bayesian workflow, frequently what will happen is that you'll use different priors and see how your estimates change based on them. And based on whether that qualitatively changes your inferences, that may speak to how stable or how strong your inferences are. So again, here's the syntax for using a BST function, Bayesian one-way repeated measures ANOVA. Again, it's outputting the model and inference data objects. And then in this case, it's a two-step process. We want to apply a sum to zero constraint on the coefficients in these ANOVA-like models, and that has to do with identifiability with respect to the parameter values. So I found it to be pretty clunky to try and do everything in one function in this case. So BST breaks up the model fitting and obeying the sum to zero constraint into two steps. And so again, we're going to diagnose our traces. I won't go over this in detail, but you can see we have healthy chains again. And now we're plotting the posterior. So beta 0 represents the baseline deflection. And here we see that 100% of the posterior is on the positive side of the reference value. So we are certain that there is a bias or a baseline deflection greater than 0, irrespective of target location. And then the target location specific deflections are indicated by beta 1, with the indexes 0 through 7 representing the individual targets. And to summarize, what I want you to take away from looking at this plot is that all of the posteriors largely overlap 0. So there's really no strong evidence that there is a target location specific effect. So it's recapitulating what we saw with the repeated measures ANOVA, but providing much more detail. And so as promised, in this example, we're also going through a posterior predictive check, which means that we're going to see how well our model retrodicts the observed data. This is a way of qualitatively examining the appropriateness of our model relative to the data. This is an important question, and one which I show you one way of how to answer below. So here I'm going to plot the behavioral data along with the posterior predictive samples. So what we're doing in order to generate the posterior predictive is we are taking samples from the posterior, random samples from the posterior, and generating which should be the putative observations based on those parameter values. So in this figure, in blue are the observed data. So again, just to orient you, on the y-axis, we have movement error. On the x-axis, we have the 8 different target locations. We can see that the posterior predictive does a fairly decent job of retrodicting the data. I would say it's not bad, but it could be better. So we see that the expected values for each target, the means of this black function, vary less than the actual observed data. It's not fluctuating as much across the different targets. And this is likely due to the sharing of information across levels within the models, those hyperparameters. So in other words, the assumption is that data at different targets should inform parameter estimates. This is in reference to using a multi-level modeling. And this results in regularization of the parameter estimates, which is frequently a good thing because it limits the variance in our estimates or the flexibility of our model, which sometimes makes better predictions for out-of-sample data. This phenomenon of reducing the variability or not allowing the expected values to fluctuate as much is referred to as shrinkage. We can, of course, redefine the hyperparameter or a model altogether to allow for greater flexibility. And so that's what I'm going to show you now. So I said several times that BST provides model scaffolding, and it's your choice how you use it in terms of you want to customize your analysis. But first, the point, shrinkage is not necessarily a bad thing. Like I said, sometimes you want to be more conservative in your parameter estimates, and pooling the data and informing different levels of the model is frequently a good thing in terms of capturing the systematic change or systematic effects, and also for predicting out-of-sample data. However, if we have a principled reason for believing that the within subject's deflections should not share information across levels, we can easily modify our model. And so that's what I'm showing you here. So if you put 2 question marks after the model name, it'll print out the model code, the source code. And then in this cell, I've copied over that code. And I'm showing you here in this line, I'm changing the definition for our sigma on A1, A1 being the target location effect. And so I'm changing it from a gamma distribution, which has its own parameters, which is informed by the other level of the model for A1. And I'm switching it to a constant. What switching it to a constant does, it essentially disrupts that connection between different levels of the model, because now there's no sharing of information. Sigma A1 is just 5. And so this essentially makes it clear that there's no sharing of information, and our assumption is that we don't assume that what happens at one target location should inform our estimates of what happens at another target location. And I'll just say, with domain knowledge, that's actually a better assumption for these types of data, that the behavior at one target tends to be independent of behavior at other targets in terms of the biasing effect. And so here we're fitting the model again. And again, it's a 2-step process, doing some algebra to obey that sum to 0 constraint, and then plotting the posteriors. And here we see the exact same parameters that I plotted above in the first iteration of the model. Again, for the most part, we see that the posteriors largely overlap 0, meaning that there's a good deal of probability density on both sides of that reference value of 0, except for maybe in the case of target 5. However, when we do the posterior predictive check again, this should encourage us, because now we see that the expected values for the posterior predictive track the observed data much better. And you can argue that the variances or the standard deviations as plotted here tend to match the observed data better without an increase in parameters in the model. So our interim conclusions are that, again, we see how Bayesian statistics provides much more information than the frequentist analog. We can conclude that there's no credible effective target at any of the 8 target locations, and we can dissect those effects with the betas for each target. So again, more information, more detailed information. BST provides a reasonable starting point for your model, and again, provides scaffolding that you can then use however you wish. You have domain knowledge of your problem, and perhaps you believe or don't believe in this sharing of information across levels of your model. And then the last point is that we can extend this example even further. So you can see here that maybe we would be justified in increasing the parameters so that we could have heterogeneous variances across the different levels of target location. But I'll save that for you to do on your own or explore on your own. And I'll just say that in example 3, we're going to do something better. We're going to model the full data set. So to pivot again, I just want to mention, as far as learning Bayesian statistics with the help of BST, as a reminder, BST is in large part bootstrapping off of another repo that converted John Krushke's textbook code into Python and PyMC3. I've updated it to PyMC4 and wrapped these models inside functions. And so they're easily reusable, they're easily printed out and easily inspected and easily modified. So I think for those reasons, they can serve as a pedagogical tool. Also, I've tested these models on the examples from the Krushke textbook, and they've been validated. So reading the Krushke textbook while following along with the notebooks that I've provided in the BST repo under the examples subdirectory can be a really nice way for Python users to learn Bayesian statistics. And then a final note, not all of the models from the textbook are included in BST as of yet. This is a work in progress, and I hope to be more comprehensive in covering the textbook in the near future. Okay, in our last example, example 3, we're going to use a Bayesian version of a mixed model design. So we're going to model both between subjects and within subjects factors on the exact same dependent variable. So we're going to assume that we've run the control analyses necessary to justify collapsing data across different targets within the same target set, meaning the near and far targets. So essentially, the within subjects factor will be target distance. And so for each subject, there'll be one observation for the near targets and one for the far targets. The goals. In this analysis, we're going to bring everything that we've learned together in order to model the effective group on movement errors, model the effect of target set, near versus far targets on movement errors. We're going to model an interaction effect, so asking the question of how the errors at different target distances depends on the group, because one may think a priori that the reach distance should affect the patient population maybe more so than the age-matched controls. That's a reasonable prediction. And so we want to test for that. And then in this example, we're going to perform contrasts between the two groups at both the near and far targets. So frequently in the frequentist paradigm, you would do an omnibus test to see, is there a main effect for this, a main effect for that, et cetera, and then depending on the p-value, then you're justified in doing these contrasts, or you're not justified, or you're justified if you do a correction for the p-value. And not to poo-poo that, but what's nice in Bayesian statistics is that we're estimating everything all at once. So when we sample and when we're estimating the parameters, we're estimating all of the parameters at each step of the MC sampling process. And so we can use those random samples to perform contrasts, any contrasts of interest. And so it's not like we're double dipping in any way. So several points of interest within this model. Note that we're, again, using a hierarchical structure. So we're going to pool information by having priors on our priors, which are indicated by these empty brackets below. Also note that the comparison we made in the first example is actually nested within this model, which I'll discuss in more detail at the end. And again, this is one of the most common experimental designs in the behavioral sciences. We have multiple groups, and each participant within each group is tested on multiple conditions. Here's our graphical model. You can see here at the bottom our likelihood function. We're representing as a normal distribution this time. You can see the uniform prior distribution on sigma, and then the deterministic component. So for mu, that's going to be a linear combination of different effects. So baseline deflection, subject-specific effect, between subjects, within subjects effects, etc. Then we have our priors on those betas, and then we have priors on our priors. So the sigmas from each of those priors on betas is associated with its own prior. Here the expected value is written out in equation form. And then I've gone through this section as far as the effect being a linear combination. So I also want to point out that BST is taking care of a lot of stuff for you under the hood. So it's parsing categorical variables for indexing. There's a reparameterization to help MC sampling, and basically keeping everything tidy so that a lot of potential pain points are removed. So here's the actual observed data. So the y-axis is the movement error, the x-axis is target distance. Just some salient points to notice. So the PD subjects shown in blue, we see that systematically they're reaching less of a distance than the age-matched controls in orange. And there might even be an interaction effect, which would be indicated by this sharper slope, or a difference in slopes across the levels between the two groups. Oh, so getting back to the first analysis with the best test, we saw that the age-matched controls generally made larger errors than PD. That's recapitulated in this figure. But I think what's very interesting is that another way of looking at that is that the PD subjects just don't reach as far as the age-matched controls, what would be considered normal. And in fact, that becomes highly problematic for the FAR target set because they're underreaching by 10 millimeters on average, whereas the age-matched controls at that point are pretty much on the money. So here you see we're fitting our BST model, the Bayesian mixed model ANOVA. Again, outputting the model and inference data objects. You see this warning error. This could be improved by reparameterization, or actually what would be more practical is changing one of these parameter values for target accept specifically. I haven't done that because the divergences are few, and so it in reality doesn't impact our posterior estimates all that much. And so, but of course, you know, that's something that you would want to explore on your own. In reality too, if I increase the target accept value, that would make it even longer to run this model, because in Colab, you can see it took several minutes running just 2 chains. On my laptop, it's faster when I'm running it in Jupyter Lab, but still, this is a fairly complex model, so it's going to take some time. But in any case, we, again, do the diagnostics as far as the MC sampling. We're okay with that for now. And then I want to note that in order to perform specific contrasts, it's going to require some knowledge of this X-array module. And so the key benefit of X-array is that it allows for convenient labeled indexing for multi-dimensional arrays. So this was something that took me a bit of time to get used to. I still don't feel completely comfortable with it in the sense that I still have to look at the documentation quite a bit. And so I've provided helpful links for you all as well as examples, example notebooks within the BST examples subdirectory. And I'm giving pointers to specific ones to check out. And then also in this example, I'm showing you how to use Xarray to perform the contrasts of interest, which in this case are to look at the effective group, the effective target set, the interaction effect, in other words, how does group effect depend on the target set, and then those specific comparisons between PD and age match controls at both the near and far targets. And so here you can see what I mean by labeled indexing. You use this Xarray function, SEL, for select, and then you can label the dimension and then just call it PD, for instance, in order to grab the data of interest. And so you don't have to remember, oh, was this in the first or second or 0th dimension? Is this a row, column? You've labeled the coordinates so that you can call them by name. And so here are the posteriors again. And now notice that the group effect is quite strong. You can see that the PD versus age match comparison, for that, the 100% of the posterior is in the negative range relative to the reference value, meaning that there is essentially no uncertainty regarding the question of whether or not PD reaches shorter than the age match controls. According to this model, 100% probability is that PD does reach shorter than age match controls. And then we have high certainty, confidence in our estimates for the target set effect as well. The interaction effect, so we see that it's mostly on one side of this reference value. I will make note that interaction terms, when you have, when you're indexing using multiple indexes, the interaction is symmetrical. So depending on which index you use, it will fall on one side or the other of 0, but the magnitude will be the exact same. The main point being that we do have strong evidence to think that there is an interaction, although there is some reason to believe that there maybe not, because we see that there's part of the posterior on the other side of the reference value of 0. And then we see the contrast for PD versus age match at the near and far targets. And now we see that nearly 100% of the probability is negative or in the negative range. And so this means that, again, PD subjects reach shorter than age match at the near targets. And then 100% of the posterior suggests that PD reach shorter than age match at the far targets. And so in this last figure, I'm plotting the observed data in a slightly different way. I'm plotting each of the individual subjects as gray lines for age matched as well as PD. And then I'm plotting the posterior predictive now in blue. And so this is the distribution that we would expect based on samples drawn from the posterior. And you can see that the model and our estimates accurately retrodict the data. And so we can be fairly confident that this is a reasonable model for the effects of PD on movement errors within the specific experimental design, or I should say, given this experimental design. So we conclude that there are highly credible differences based on group and target set. And I would say there is credibility in terms of an interaction, but not quite as robust as the other effects. The participants with PD showed a strong tendency to reach shorter distances than the age match controls, which was especially pronounced at the far targets. I want you to take note that there's a reduction in uncertainty around the difference between PD versus age match at the near targets in comparison to the best test in example 1. So I'm referring to this contrast specifically. This occurs due to the pooling of data for more accurate estimates. as well as this being a finer grained analysis, because we're parsing out the effects of not only group, but also subject, target set, and interaction as well. So we can get a better estimate of that group specific effect. Oh, and also notice that I subtracted the age match values from the PD values in this case, as compared to doing it the opposite way in example 1. And I did that just to highlight the hypometric errors made by the PD group. And just a reminder, BST takes a lot of the pain out of fitting a fairly complex model, at least in terms of the fitting process. All right, so just some final thoughts and a bit of summary. So we saw that BST provides you with helpful tools for utilizing and exploring Bayesian statistics right away within your own research projects. We also saw that the BST repo provides notebooks covering examples from the great textbook Doing Bayesian Data Analysis. So in this way, it can really serve as a useful pedagogical tool as well. So you can go through the textbook and see how to write the models in Python and PyMC using BST. Also, just a plug to check out Bambi for a more advanced Bayesian modeling interface. I also want to say that BST, as we saw, is intended to be part of an open and replicable workflow. And across these examples, we showed many of the most important steps involved in Bayesian data analysis. So we started with the generative or graphical model. We fit our model to the data, and we analyzed the health of our MCMC chains. We also discussed and saw posterior predictive checks and how to visualize the posterior distributions. However, we did not discuss today prior predictive checks or model selection, which is also an important part of a Bayesian workflow, but something that we just didn't have time for within this talk. So I want to remind you that BST is still in early stages, and so I have a lot of plans to introduce new models as well as notebooks on things such as Bayes factors, how to do a Bayesian meta-analysis, and how to do a Bayesian spectral analysis. So this would be looking at responses to sinusoidal inputs and analyzing the data in the frequency as opposed to time domain. And a reminder to please follow the BST repository on GitHub and follow me on Twitter. We'll be updating the BST repo on a regular basis in the very near future, and there's going to be some exciting changes and improvements as well. So another reminder, the full instructions for how to install BST on your local laptop is provided on GitHub. However, we do have plans to add BST to PyPy fairly soon in order to make installing BST a breeze from anywhere. And also a final reminder to join the discussion now over at Discourse to ask questions and propose suggestions and let us know your comments and thoughts on BST and this talk. And I'll be hanging out there for a while. And so thank you again, and I'm looking forward to hearing your questions as well as suggestions.